Hey everybody, Dr. A here, and in this video we're going to be providing some background information on the boiling potential in sands downstream of geostructures. Now, the idea behind this is similar and a little bit related to one of the other videos when we looked at heave potential on the downstream side of sheet pile walls, but it is a little bit different and it's got some of its own unique attributes. So let's go ahead and get started. So we're going to say for geostructures founded in sands that are experiencing seepage, boiling occurs if the maximum exit hydraulic gradient is larger than the critical hydraulic gradient. So before we go past that line here, the first thing we want to remind ourselves of is what is boiling? Well, boiling is the term that is used for a loss of stability in sandy soils. So when boiling occurs in sandy soils, that means that your effective stress has gone to zero and you have a loss of stability. So for clays and silts, the term you typically use is heave. For sands, you use the word boiling, okay? And again, it occurs when the maximum exit hydraulic gradient is bigger than the critical hydraulic gradient. So we can develop a factor of safety against boiling as the critical hydraulic gradient divided by the maximum exit hydraulic gradient, okay? Now, we define this here. The I exit max is the maximum exit hydraulic gradient, and this is on the downstream side of a geostructure. And that's typically equal to what's called delta H over L min, okay? So that brings me to the question, what is delta H? Well, delta H is the change in head. So that's basically the head loss. So we can put a little comma here. Delta H is the head loss, okay? And then L min is the shortest length traveled, all right? So let's look at a little illustration of this. Let's consider that we have a water level here, okay? And let's say that we have some kind of geostructure. I'm going to make it a concrete dam for us, okay? So let's say this is a concrete dam, and we'll put some little triangles here for hatching purposes. And let's put a ground surface here and here. And let's say that on the downstream side, the water level is at the same level as the ground surface. Okay, so again, this is just for illustrative purposes, all right? And then we're going to say that this water level here is going to be maybe a height capital H, okay? And so the first question is, in this situation, what would be the head loss or the change in head? Well, the way we get that is we would need to develop a flow net, okay? So let's go ahead and finish drawing this nice little figure here. Let's say that this is the impermeable layer, okay? So the first thing you would need is information about the flow net. So I'm going to go ahead and sketch a flow net, okay? So if you remember, these are called flow lines. And then we're going to have equipotential lines, okay, that look something like this. Okay, so something like that, nice flow net, all right? And so we know that the water is going to be flowing from upstream to downstream, all right? So what we would do is we would first go ahead and get that head loss, that delta H. So how would we do that? Well, we would say delta H equals the change in head over the number of drops. So in this case, we would say the change in head is just capital H because we said on the downstream side, the water level is at the ground level. So the numerator of this head loss is going to be just that capital H, and then we're going to divide by the number of drops, okay? And so what this is going to give us is, the head loss per drop, basically, all right? And so from there, we use that term as the numerator of I exit maximum, all right? What about L min? Well, this is the shortest length traveled, all right? And so typically what you do for L min is you look at this length, we'll call this L min. You look at this length, which is the shortest path traveled on the downstream side, okay? So I'll put a note here, downstream side. Now, specifically, this is going to be the dimension of this flow element, okay? It's the dimension of the last flow element that's adjacent to the concrete structure, okay? So that's this vertical dimension right here. And again, it's shortest length traveled on the downstream side in the last flow element, because again, this is where you're going to lose the stability, because remember, the water is flowing in this direction. So where are you going to lose stability? Where you're going to lose stability right here at the toe of that dam, okay? So you can physically measure this using software, or maybe you have a scale factor on a handwritten problem. Regardless, you get this physical dimension, all right? So this will have units of length, and then delta H also has units of length, all right? So you calculate that I exit max. Now, what about the critical hydraulic gradient? Well, I critical is going to be equal to G sub S minus 1 over 1 plus E, okay? And so that's your critical hydraulic gradient, and that is what goes in the numerator of that factor of safety against boiling, all right? So that's the background information on this topic. If you're looking for some good numerical examples of situations like this that you can read on your own, you would find those in a lot of great geotechnical engineering textbooks, but this video is just meant to provide some general background information on the topic. So if you found this video helpful, please hit like and subscribe.